I'm going to walk through how to calculate a chi-square test for independence. And I'm going to use the in-class activity that is available in Module 4. And I'm going to specifically use the Research Study 1. So I have the data set up, but on the in-class activity it does not show the data set up like this. What it does is it gives you a research scenario, and you have to kind of figure out what's going on. So the key to this being a chi-square test for independence is that there's two independent variables. So the first being basically that you have one variable with two categories related to personality. And then you have two categories related to number of siblings. Either you're an only child or you have one or more siblings. So that's the two independent variables. And so each of these has two categories. So you know it's a 2 by 2. And then it gives you kind of information you have to piece together. So it says a sample of 100 participants is obtained. So you know out of the entire study there's 100 participants. There's 50 only child participants and 50 people who have one or more siblings. And then it talks about how after they completed personality assessments, it shows that 17 of the 50 only child participants scored as outgoing. So I immediately put in 17 in the outgoing only child. And then it talked about showing 28 of the 50 one or more siblings scored as outgoing. So then I put 28 here. Now I obtained these two by just taking 28 and subtracting that from 50, and the remainder goes here. So you know if 28 of the 50 were outgoing and they had siblings, you know that the remaining is 50, or the remaining adds up to 50. So the rest of them were reserved. And then same with the only child. We were given 17 who were outgoing, the remainder were reserved. So that's how I completed that 2 by 2. You just kind of have to work through it and figure out what are your variables, how many categories are in each variable, and then just start kind of plugging things in. So the first step obviously would be stating our hypotheses, and again, chi-square test for independence just looks for relationships. So a basic alternative hypothesis would be that there is not a relationship between personality and number of siblings. It's as simple as that. Then we're going to need to get our critical value. And if you recall, to get our degrees of freedom, it is, k minus 1, and that's for group 1, times k for group 2 minus 1. And k is basically, the number of categories, or the number of groups. So with this, we end up, 2 minus 1 is 1, 2 minus 1 is 1, so our degrees of freedom is 1. We looked that up, 0.05, and you should end up with a chi-square critical value, which equals 3.84. So this is our critical value that we're going to be testing against. Now, we're going to need to get our expected frequencies to be able to complete our chi-square. So if you recall, we're going to need to get our row marginals and column marginals to be able to complete that. So we're going to move to the next slide so we can have some room to do that. Okay, so next slide. So I have my table, and if you've noticed, I have basically highlighted what cells I'm focusing on by numbering them. So if you notice, like I have cell 1, cell 2, cell 3, and cell 4. This is so that I can just keep track of things. So we're going to first get our row marginals and column marginals. So basically, if we look, here's like what you would call your rows, your row marginals. So you're just going to add up across 33 plus 22. That's 55. Because that's the row, right? That's when you go across, that's a row. Then the second one, 17 plus 28 is 45. Then we're going to get our column marginals. So that's those columns. So when you go down, that's a column. So 33 plus 17 is 50. And then 28 plus 22 is 50. That makes sense because if you remember in the initial research scenario, it talks about how they obtained 50 people with one or more siblings and 50 people that were only children or only child. So you know there's going to be 50 and 50. No matter what, if you add up the row marginals or the column marginals, you're going to get 100. This is basically your N. That's the total number of participants in the entire study, N. So now we're going to work on getting our expected values. So to get those expected values, I just kind of organize things. So I'm going to work on just cell 1. If you notice, it's the equation above, f of e, for cell 1, is the column marginal or frequency times row frequency divided by n. So I'm going to do 50 times 55 divided by 100. Now, if you look, how this is done, I'm just going to line things up. If you notice, like for row 1, which I'm working on right here, okay, I'm going to line it up. What is its column marginal? Well, you look down here, it's 50, okay? Then if you look over, its row marginal is 55, so that's what I'm going to use, and then divide by the total n. So that's how I'm obtaining these numbers. So now, if you do the math for that, you should get 27.5. Oops, 7.5. Now we're going to go to the expected frequency for cell 2. And again, I'm going to, look at cell 2 right here, and I'm going to look down. Here's its column marginal, 50. Here's its row marginal, 55, and the n is 100. So it's repetitive, especially when you have a 2 by 2. It's very repetitive. So, we're going to do the same thing again. 50 times 55 divided by 100, and we know that's 27.5. So now we can look at cell 3. So again, when we look at cell 3, we're going to look at, okay, here's cell 3, here's its column marginal, here's its row marginal, and here's the n. So 50 times 45 divided by 100. So f of e equals 50 times 45 divided by 100. And you should get 22.5. Same thing for cell 4. And it's repetitive again because the column marginal and row marginal are the same. So it's 50 times 45 divided by 100 equals 22.5. So now we have all of our expected values to be able to actually calculate our chi-square. So if you recall, I'm going to write it up here, our chi-square equation is f of O minus f of E in parentheses squared divided by f of e. So we're going to have 4 chi-squares that we're adding together because we have 4 cells. So here's what we're going to be looking at. So f of O for cell 1 is 33 minus, and the f of E for cell 1, the frequency of the expected value, is 27.5. 27.5. We're going to put that in parentheses squared divided by 100. Oops, sorry, not 100. Let's go back. We're going to erase that. Divided by 27.5. I was still working on expected values in my mind. So again, it's divided by the expected value. Now we're going to add that to the next cell. So cell 2, the observed frequency is 22, expected frequency is 27.5 squared divided by 27.5. Now we can do cell 3. So cell 3 is 17. Its expected frequency is 22.5. N squared over 22.5. And then the last cell we'll add, I'm kind of doing a running log here, cell 4's observed frequency is 28 minus our expected frequency is 22.5 squared divided by 22.5. Okay, so you have your 4 chi-squares there that you're going to add together. Because remember, I'm sorry I didn't put it on here, but there's a summation there. So you should be summing those together. So once you add all of those together, you should get a final chi-square of 4.889 is your final chi-square. So before we decide whether it's significant or not, let's calculate an effect size. Again, this is a 2 by 2. So our effect size is going to be our phi coefficient. We're going to be using a phi coefficient because it's a 2 by 2. So let's go to the next slide. Our chi-square, I'm just going to write that here, chi-square equals 4.889. Now we're going to use our phi coefficient for effect size. So that's chi squared over n, and take the square root of that. Now this n is the same thing as capital N, basically. So if you look, our n was 100. So to put 100, and chi-square is literally your obtained test statistic. So 4.889. All of that under square root. You should end up with 0.22. So there's our effect size, 0.22. Now to determine whether we have significance or not, we need to see where the test statistic falls compared to our critical boundary. So let's go back to the beginning, if you remember. Here's our critical value, 3.84, with the degrees of freedom of 1. So we're going to go right here, 3.84. Now, similar to ANOVA, chi-square is always positive. It's not plus or minus, it's always positive. So anything that falls beyond is significant. 4.889 would fall somewhere over here. So it is significant. And I just put F critical value, and because I'm still thinking of ANOVA, that's a mistake. It's the chi-square critical value, and this is our chi-square obtained value. So now we know we have a significant test with a phi coefficient of 0.22, looking at the relationship between number of siblings, and personality. So we're going to write our results. And it's a pretty simple and APA format. So I'm going to write, there was a significant relationship between number of siblings and personality. You can just use like a blanket, that umbrella term for your independent variable categories as, we're going to say chi-square, and in parentheses we're going to put our degree of freedom that we use to look up our critical value, and then n equals 100, and our obtained test statistic rounded to 2 decimals, 4.89. P is less than 0.05, that was the alpha we used. And if you remember, our phi coefficient equaled 0.22. And that's it. That is our APA results and how to calculate the chi-square test for independence.